Hey everyone, welcome and thank you so much for joining us today for an interesting webinar on how to leverage your AMI system to improve distribution system reliability by Bridgewater Consulting Group, Itron, and myself from CIADI. My name is Ari Kellenson. I'm the program manager in CIADI in the transmission and distribution sector, managing 5 programs. Just to let you know, in order to ensure good audio quality, all attendees are muted by default. If there are any questions, please type them in the questions box below. If you could see in the graphical user interface, there is questions chat. So the chat box could be used for any audio or visual technical issues that you're experiencing, and one of our coordinators will be happy to assist you together with our IT department. The questions box is for you to ask technical questions or questions related to the webinar content. And when we have time at the end, there will be a Q&A session, and I'll be happy to address as many questions as I can. If I won't have sufficient time to address all questions, don't worry. All of these questions are logged within the webinar platform, and we'll definitely follow up by email and make sure to address your questions, okay? I'll just wait another 2 or 3 minutes for some of the remaining of registrants. As you guys know, it's taking some time for everybody to be fully registered, and we'll start soon, okay? Just approving some more. Okay, so let's start. So a little bit about CIADI. CIADI is a user-driven organization committed to providing technological solution and knowledge exchange to power utility members all over the world. Essentially, we provide a collaborative framework which facilitates the information exchange and knowledge transfer between utility participants as well as subject matter experts such as today's from Bridgewater Consulting Group and Itron. Part of our work, our collaborative initiatives manifest themselves with a form of collaborative projects, industry benchmarking, and technical training. Looking at our projects, they're very practical, short-paced in nature. Essentially, utility participants can not only share project costs, but also get a wider perspective from many international utility experts, contractors, vendors, university professors, and so on and so forth. Member utilities can assign project monitors to make sure that the project is relevant to their needs and supervise the project progression milestone by milestone. Industry benchmarking is essentially us allowing utility engineers and specialists in the field to ask questions, and then we circulate a survey with all the questions and answers to all of their members, and that's available on my CIADI portal. So within 1 or 2 weeks, you get a good idea of what other utility engineers are doing in that space, and looking at best practices and so on and so forth. Technical training like today is essentially CIADI's, together with the members, select and approach presenters from all over the world, such as contractor, vendors, university professor, and so on and so forth, to provide a training, technical webinar, workshop, best practices guideline, best tools, softwares, and so on. And all of that is recorded and available to our members. In CIADI, we have 150 member utilities from 18 countries worldwide. Our makeup is about 50% from the United States, 30% from Canada, and 20% from overseas. We also have 22 distinct programs covering vertical power from generation on the left-hand side to transmission and distribution. This webinar will be mostly relevant to the Smart Grid program, distribution line asset management program, power quality and advanced technology program, as well as protection and control when we look at advancement in AMI technologies. And the presenter will be happy to discuss that in more detail shortly. I'd like to introduce our today's presenters From Bridgewater Consulting Group, we have David Grace. He's the Advanced Analytic Practice Lead who has deep technical background and expertise in AMI technologies, substation automation, power system data integration architecture, as well as power quality. He has an extensive engineering utility experience, he was the general and project manager for Southern California Edison's AMI operation centers. Aside from that, David has 2 patents that he's very proud of, that every time we're having a virtual meeting, he makes sure that they are clearly noticeable in the background on the wall behind him. David also provided a webinar within CIADI last summer, which explains how to leverage AMI system to improve T&D operations. So just to provide a quick recap, today's presentation is to look at system reliability, focusing on distribution systems. Of course, they have the capacity and capabilities to elaborate also on the transmission operation, but generally speaking, following up on the previous webinar, our members indicated their interest, and we had a call and discussed, what will be useful and valuable for the members. So that's how we drafted today's webinar. From Itron, we have, I'd like to introduce you to John Lamp, who is the Director of Business Development and has quite extensive technical background with AMI system technologies, as well as with utility AMI practices. John is an early pioneer of the Internet of Things and have created leading technological products in smart grid design space since 2001. His utility experience also includes being principal of Lamp Consulting, where he helped Southern California Edison lead smart grid design and roles as a VP Strategic Engagement of Trilent Networks and CEO of AIP Solution. So without further ado, I'd like to invite David Grace from Bridgewater Consulting Group to provide another interesting presentation. So David, I'll hand it over to you now to provide a quick overview on Bridgewater Consulting Group as well as Itron. I'm just going to set you a presenter here. Here we are. You can see your screen.
All right. Thanks. I thought you were going to leave that joke out. Anyway. Hey, I was just there. Yeah, I know. First of all, I want to show my appreciation for those that are attending this, taking your valuable time and, to spend an hour and a half with us. And so thanks very much, especially those that have been with me. I see some of the names that I know and I'm just surprised they're on. So I'm grateful for everybody attending. So we're going to go through 2 quick slides on the companies. And the first is Bridgewater, and I've been with them for 2 years. And it was founded by Mark Montgomery, and he had really 2 visions. One was that he wanted to bring together people with utility experience. We have over 150 employees, where the vast majority, have direct utility experience in gas, water, and electricity. And the second part is relationships, that we have strong relationships with our customers. So we have a number of practices in business strategy, customer experience, utility modernization, and we're going to go into the advanced T&D analytics. So that's Bridgewater, and they're based in California, but have offices other places. Itron, we have a strong relationship with Itron, and this has been going on for a year of developing this, where Itron, they are a leader in meters, AMI systems, and those systems were really used for meters to cash, generating the bill. The future is the smart grid and using and leveraging that infrastructure for T&D. So we joined up that we have experience in, SCADA, DMS, EMS, the actual distribution operations, and we also have experience in AMI. So linking up with Itron made a lot of sense, and Itron has developed a whole division dedicated called Outcomes. Fred and Wasim, we deal almost daily with making sure that if you get an AMI system, it delivers the expected benefits, not just putting data in a database. So that's the changes that are going on with Itron. That's why we've hooked up together. and trying to ensure that that infrastructure is leveraged. So without further ado, let's get into the webinar, and hopefully it'll provide some insight. So the title of the webinar is Leveraging AMI to Improve Distribution System Reliability. So it's taking the AMI system, and we'll get into it. A lot of you aren't that familiar with AMI, so we're gonna deal with some blocking and tackling, some basics. But the focus is on distribution system reliability. The agenda is we'll go into AMI measurements. What does it measure? How does it communicate? Then we'll go into specific use cases associated with distribution reliability. Now, the use cases, we also have to talk about the architecture. Just by having meters issue data and stuff doesn't get you where you want to go. So we're going to talk about how you really get it implemented. One of the questions that came up by the members of CIADI was, hey, can we use the cell routers for distribution communications? We're going to talk about that. As a matter of fact, John Lamp will do that. And then later on, we'll have a thing on offerings and a Q&A session. So that's basically the agenda. AMI systems. The webinar will describe on how to untap the data. AMI data communications, how the system can be leveraged with use cases, architectures, and cell routers. What I want to emphasize is that the webinar's content is not pie in the sky. This has been worked on. We've had research, we've piloted, code's been written, and it can be operationally implemented. So I want to ensure that you're not just getting, oh, maybe if we can do. A lot of this stuff has been researched and piloted. All right, reliability. So again, we're talking to folks in T&D and operations engineering, advanced technologies that may not have the background in AMI. So when we're talking about reliability, I want to define it. So number one, we're looking at AMI to help improve restoration. So in my work in distribution, it's identifying faults quicker and their footprints, especially sub-circuit faults. When a breaker opens up, you pretty much know where the fault is, but it's things that happen within the circuit. More precise location identification, really important. Optimize switching. So when you know the location and everything, can you switch to minimize the footprint? Reduce faults. Can you predict problems that cause faults? Distribution equipment failures. Identify anomalies that are precursors to a fault. That's an area of improving reliability. Prevent severe power quality incidents. Reliability is based upon power, they're related. Power quality is the ability of a customer's load to perform as expected. So can we prevent severe power quality incidents, voltage problems, other problems like that? And finally, safety. Brought that in. So the fast identification and mitigation of energized now conductors. We'll talk about that. And in the West Coast here, we have a thing on wildfires that are related. Now, how do you measure them? SAIDI is the biggie. So SAIDI is your average duration per customer, and that's the biggie of measuring it. Management KPIs also, your management has KPIs and then PUC agreements. So that is where we're coming from. That's the basis. We're going to talk about the applications, and these are the applications. I'm just going to run through them real quick at this point. Advanced OMS, how to identify that footprint, where it is. Energized now conductor, also called high impedance fault detection. Support voltage control to avoid power quality issues. How to deal with residential solar and charger issues that are causing major problems today. Predicting failures and supporting ADMS and distribution automation. Those are the use cases we'll talk about. So AMI is your new grid sensor. And here's the ABCs. What do they measure? Well, KW delivered, KW received. These are net energy meters that'll look at power going into a house and power coming out of a house due to solar. Voltage, very unused component, but the meters do measure voltage. Power outage information, power restoration information. Now, when it's measuring things, you have to give it an interval. So an interval can be this notion of an average. And this applies to many different types of vendors and equipment, but you give it an average. And so for example, kW, voltage is averaged over this interval that you give it, but it also meters do instantaneous stuff. So for example, the meters that I worked with looked at instantaneous voltage. What is it? 1 second RMS values every second, where the meters also look at that. How do you get the data? Well, reading data, you can do what's called a broadcast. You know, you have a group out there, you send out a message and say, give me your data. And you give it an interval. We'll talk about that a little bit more, but you know, all the meters don't respond instantly, they respond over a period of time. So you can read data as a broadcast. You can read it point to point. You can go to specific, you know, ESNs or serial numbers and say, give me your data, or you can go to do an interactive read. That means you can connect to a meter and say, what's your voltage? What's your kW? So these are different methods of getting data. Now, the meter can also do initiated exception data. What's that mean? That means that the meter can send out information on its own, outage information. We call them PONs and PERNs, power outage notification, last gasp it's also called. You're not asking for it, the meter automatically sends it out. Well, how about when the voltage exceeds preset limits? Yep, the meter can send out this thing called an exception. You can call it a notification, we're just using the word exception. And also for those that are familiar, remote service switches. You know, you send out one and it sends back, yep, I did it or I failed. So meter initiated things can happen. And that's the way we get data from meters. I want to go over that interval business on voltage because a lot of the work that we're doing in the distribution area relies on voltage data from the meter. So this notion of interval voltage, well, you can give it any kind of interval, 10 minutes, an hour, whatever it is, you set it. What does it do during that time? Again, it depends upon the vendor, but many meters give you the average voltage over that interval and the minimum and maximum during that interval. What's the min? That's the 1 second or 5 second, whatever it is. So those values, you can set up the meter and then you can store it in a log. So there now every, you know, if it's an hour, every hour it'll store max, min, and the average during the hour. You're going to put up thresholds, and if it exceeds those thresholds at the end of the hour, it'll store it in a log, and the meter can send out an exception to say, ooh, I went past the threshold. That's your typical interval voltage. Now, the meters, untapped, also can look at voltage continuously. So we call it VRMS voltage. You can set it for 1 second, 3 seconds, but every second the meter will look at the RMS voltage. Compare it against thresholds. This is 1 second values. That's pretty good. It's not a power quality meter, you know, the cycle analysis, but it can do pretty a short interval kind of measurements. So the cool thing is, it'll compare it against thresholds, and if it exceeds, it'll store it in the event log, but it can also send out a real-time exception. So on a 240 volt meter, you say, hey, when it ever drops below 180 volts RMS for 1 second, it'll send out an exception. So that becomes very powerful in the way of using this data for distribution. Now, meters are highly accurate. I see a number there, but I think it's more accurate than that. So we'll have to go back during Q&A. But meter, the voltage of a meter, the accuracy is very, very high, especially when you compare it against, you know, substation data. It's very accurate. Now, here we go to in basically communications. Here's a simplified AMI data architecture. The meters hop. This is an RF LAN. But meter data hops from one to another. It goes back to a cell router. You might have 500, 1,000 meters to a cell router. And then it goes back through a public or private carrier to the head-end system. All right. Then it goes into some kind of temporary storage because the head-end system is not usually a database. Well, from the temporary storage, the data you're familiar with, the interval data, usage data goes to the MDM, and the other meter data goes to a meter database. generally you do batch analysis on that data. So you don't usually do batch analysis on the MDM. Hey, that's meant for billing. Don't touch it. But all the voltage data, logs, and everything go to this other meter database. Then you get the exceptions, and right now they're coming directly in. They don't go through that system, but they go to different types of operational systems. For example, if a security exception comes in, it'll go to a security monitoring system. If an outage exception comes in, it'll go to OMS. So this is your typical layout. Now, RF LAN communications, they do have some limitations. Latency. So to give you an idea, you can have, depending upon how many hops the meter, it can be 10 seconds before data comes back from a meter to the head-end system. Okay? So that's number one. Many times it's quicker, but it can take that long. When you do major read requests, you have to do an interval. So that interval can be 5 minutes, 10 minutes. So, you can have a latency of information coming back. And also there's ETL, extract, transform, and load process by the time it gets to the database. So there are inherently some limitations. Loading constraints, not too bad because it's dependent upon the cell router, but loading is you can't ask the data consistently. And then to address loading constraints, you can implement threshold exceptions that we talked about, or bellwethers. Bellwethers are meters that represent an area where you can read them every couple of minutes, and it gives you a handle on what's going on in that particular community. So you don't have to read all meters. So hopefully that gives you an idea of what the meters measure and how it communicates. So the communication is not what you're familiar with in DA, distribution automation, or SCADA. It takes a bit of time, but it can be used effectively by doing some things we'll talk about later in the architecture. All right, we are on time, and we're going to go into reliability associated use cases. And to underscore, these have been researched and piloted. The first one, and I've been on IEEE committees and been involved with this for lots of times, is the wire down, the energized down conductor, high impedance fault. Well, in the West Coast here, we did a lot of work and we found out, yeah, we can identify wire downs with pretty good accuracy in near real time. We have a 3-wire system out here, but this is also can work on a 4-wire, but a lot of the work that I did is on 3-wire systems. So when a wire goes down on a 3-wire system, you're looking at an example of a 12 kV, for example. There's the load side wire down. When the load side wire down, those meters that are connected to transformers, they don't go to 0. They go to the square root of 3, or if you're a 240 volt meter, it goes to 138 volts. If it's a source side, on the other side, it's a voltage divider, and the voltage will go down to 120 volts, or thereabout. Now, it's not exact, right? It can go down to 130, 150, whatever it is, but it's an indicator that you have a wire down. Now, we've developed analytics, fairly extensive analytics that'll determine, if you, with a degree of confidence, you have an energized down conductor. It's been tested on many, over 500 cases, and we have a pretty good handle on it. So on 4-wire, there's a different set of analytics, but it can also be done on this. One of the applications of this is wildfire. So in the West Coast, the idea if a wire goes down in a wildfire area, that is a signal to us to respond. But really the driver in this is public safety. Do you have an energized down conductor? And when you go on to your logs at the utility, you'll find, it's maybe 1 out of 7 that's actually maybe even more, 1 out of 10 that's an actually energized down conductor, because you get these 911 calls and everything in there. They can be communications down or whatever. But, they don't occur as frequently, but when they do, they need to be addressed rapidly. So analytics have been developed for it. This was one example that we showed at Distributech jointly I did with Southern California Edison. And this was at a location. And this was an interesting one where the truck went out and repaired a blown tap, and then the truck left. And then in the morning, the truck happened to be there, and somebody came out and said, hey, there's a sparking wire in my backyard. So for 10 hours, that wire was down. And you can look at the voltages, 247, 149, 140. Ooh, that's your load side voltage. And, you know, it was repaired, but it was a wake-up call. So anyway, the analytics have been developed. I know Southern Cal is doing a bunch of work on it. And but in order to really determine the confidence, there are a bunch of other rules associated with it, like what's happening downstream from the location, what is the voltage, you know, there's a bunch of rules to improve the confidence of it. But the energized down conductor has a particular signature. That's one use case. Another use case that we have is the outage footprint identification. Now, we were getting PONs, but we weren't getting PONs, power outage notifications, at a couple of utilities, but they were coming in, you know, only a portion of them. They were coming in a little bit later. We were still relying on phone calls to do the major portion of the analytics in OMS. But we determined that by doing perimeter analysis, we could get a 95% accuracy on where the fault was and what's the footprint. And the reason is that, you know, meters, when you have the connectivity model associated with it, a lot of meters can't respond, because if they are sending out a notification and the meter in front of it is also, that meter's not going to listen to that power. But if that meter is talking to another meter that's not part of the outage, that meter can listen and pass on the notification. So by knowing the network configuration, the connectivity model, getting those initial power outage notice, and just doing simple algorithms of perimeter analysis, you can get a fairly good handle on where the fault is and what is the footprint. So without having to wait for a full set of phone calls to come in, but using the PON. So it's overcoming some of the limitations that folks learned of the power outage notification last gasp, and it works fairly well with a high degree of accuracy very quickly. So that's just another use case that was done. The next use case is identify the voltage impact of residential solar. This was an interesting one because many utilities are experiencing higher and higher penetrations of residential solar. Okay, so we're not talking about, you know, major transmission DER. We're talking about residential solar that have this thing called the inverter. So utilities during warm days and everything, you manage voltage, trying to keep voltage in a Rule 2 level or in a nice sensible level by using tap changes on transformers, capacitors, sometimes switching load, and that's your method. What do we always expect? So for years and years, we saw high voltage at the substation, went down to medium voltage, and then low voltage in the neighborhood, basically due to I²R losses in the conductor and to heavier loads. So what you do is you increase voltage at the capacitors and, you know, trying to boost the voltage at the neighborhoods. Well, the game changer was that we started to see high voltage at the sub, medium voltage, and then very high voltage in some of these neighborhoods. And the situation was that these residential solar inverters would kick up voltage. Like pressure, they had to increase voltage to push energy. I'll use an example, but push energy back into the system. So the voltage became, you know, as the penetration increased, the voltages became much higher. So what you saw during these periods wasn't where we were expecting low voltage, we saw high voltage. And you got to a point where the inverters would shut down under high voltage, which would cause issues with the customers because they wanted their inverters to work and to enjoy the, you know, the benefits of their residential solar, and they weren't getting it. So, and also the high voltage would cause problems with equipment. Obviously, reduce loss of life. So high voltage is not a good thing. So by using simple bellwether analytics, you have to do a little work to come up with the notion of the bellwether. Reading a meter every couple of minutes in a neighborhood that represents the neighborhood is a little bit of work to pick out that meter and also to maintain it if you make that into a bellwether. So, but you can read those meters on a regular basis, not impact loading, have no effect on billing in your system, and you get a pretty good handle in near real time if you're having a residential solar issue, and your response obviously would be to open up the capacitor or do things to get the voltage in that area. But the first thing is see what you got, because I think you'll be surprised of some of the numbers. Now, the meters can do this, as I mentioned. Yes, you can either do a bellwether or set up thresholds, but the bellwethers seem to be the most realistic thing, and the coding for doing that, the algorithms are pretty straightforward. Another use case is predicting problems with equipment. So what you're looking at here is a very simple thing you can do to predict a distribution transformer failure. So what you'll see is you're looking at voltage over time, and the voltage is bouncing around during the course of the day as the loading 24-hour, and all of a sudden the voltage jumps. Ooh, that step change in voltage is your simple indicator. If it goes up, that's a winding to winding short in the secondary. If it drops, it's a winding to winding short in the primary. So these winding to winding shorts, are precursors. The transformer will not often fail, but it gives you a handle on, you better go out and do something about it, especially if it's in, let's say, a wildfire area or a highly populated area. We don't want a catastrophic transformer failure. But again, the algorithm's pretty simple to do, and I'm pretty sure that Itron has that algorithm built in to their OO system. That's operational optimization, their system. This is a really interesting one. I did the work on this, and it's not totally complete, but yeah, it was okay. So anyway, what this is about is predicting a cable or conductor failure. Now, underground cable failures are a major factor in safety. They're really hard to find, hard to fix. And if you can predict their failure and fix it, that really makes a difference. And overhead conductor failure, same thing. Especially if it's in a wildfire area or a populated area, you want to get a handle on it. So the failures, a portion of the failures are due to, let me call it mechanical. Corrosion, loose connections. Not all of them, especially underground. You'll get treen and the insulation and stuff like that. Meters can't do anything about that. That's too high frequency. So, but if it's a mechanical or something, can we predict a issue with an elbow, with a connector? Can we issue? And the answer is, to a degree, yes. You see some examples there of this is a plot. Now, I don't want to say it's a voltage plot, because you're trying to look at meter voltage and trying to extrapolate up to a 12 kV. So you have to take out a lot of factors. You have to take out, the loading on the meter. What you're trying to do is, normalize it to say what's happening at the 12 kV, even though you're on a 240. All right. So we developed a series of analytics to filter out that, group meters, do standard deviation, statistical analysis, and come up with a plot that says, wow, yeah, there was some issues prior to the failure. So luckily I had failures, and I was able to go back and see, were there precursors to the failures? And there was, in a chunk of cases. And it was around 20–25%. Now, what I didn't do is do false positive analysis. So this was analysis on known failures, but I haven't done the, false positive. When do you get these when there isn't a imminent failure? So that has to be done, but it's pretty good. Now, a couple of utilities have done the work on their own, and John told me from that Southern company, and I'm sorry if I'm misstating it, but I believe they've done work and came up with pretty accurate algorithms. We don't have those algorithms, but our algorithms, I would expect, match theirs pretty well. But I think at a major utility, they did the work and thoroughly and came up with that. Yeah, you can use metering data to predict failures. So that to me, in terms of reliability, is really pretty interesting, and you know, it's very worthwhile to look into. The next one is when we're talking about the smart grid, distribution automation, the modern grid. What we're trying to do is use modern techniques to improve reliability, to improve safety, to reduce losses, to do all kinds of good things. Now, a lot of those activities had to do with doing a load flow model in real time. Load flow models, we all know that they have limitations. They're expecting, a lot of them are based upon, the estimation is based upon impedances of wires and all kinds of things, and a known circuit connection that may have changed over time down at the residential level. Well, what happens if you have a bunch of bellwethers and you start looking at them? Now, if you do that, you'll get a very precise, much more precise load flow model. You can put it into the load flow model as opposed to just estimating what the values are, especially at the ends of radials. Now, again, the bellwethers, a minute or two and stuff, so that's okay when you're doing load switching, or when you're doing fault restoration, or when you're doing, you know, when you want to do a scheduled outage. You can optimize your switching based upon the bellwether data and, of course, historical information. So you want to, you know, say, what are we reading now? What do we expect an hour from now? And then do much more precise switching to improve load flow and to improve distribution automation, which improves, obviously, reliability and your SAIDI numbers. So those were a series of use cases that we wanted to present today. There are others, and we have some on scheduled to do, but that'll give you an overview on the use cases. And what's interesting there is it can be done on a lot of different vendors. While I was focused more on Itron, they are doable, and they have been researched. So during Q&A, if you have any questions about those use cases or a thought for another, we are open to it. And remember, under the Q&A, that if we don't get to you, it will be written down and we will respond to you, to all questions. All right. Data architectures to support the T&D applications. So it's one thing of data from an AMI system going into a database, but can you really enjoy the benefits, you know, if you can't take action, if it's not actionable intelligence, and it's not integrated with your system? So in utilities I worked with, the architectures needed to be reviewed and in some cases modified to support AMI. So if you're going to leverage AMI, you have to have a upstream architecture to support it. And that's what we're going to talk about now, because it really is important. So we're going back to our old diagram of, this is the old AMI system, and you can see, you know, exceptions going to an OMS system. And in many cases, those have to be baked, you know, because you get duplicates. So many utilities will hold them for a few minutes before you even dump it to the OMS. The other data goes into a metering database, and there's a lot of latency, so you're really only doing batch analysis. So this architecture was good for meters to cache and to some basic things, but you know, the use cases that we talked about has to be looked at a little bit differently. So what's the constraints of existing architectures? And this is really important. I've been involved in architectures and substation and data automation for a long time, and the architectures are sometimes overlooked. So constraints of existing architectures, delays in exposing data. So the idea that if you're going to use the data, but it comes in too late for the intended application, that's a deal killer. So, but there are delays, and some of these delays come from, well, the data gets into the head-end system, and then they go through ETLs where the data doesn't show up in the database until 15 minutes, half an hour later. Often the case. Blackout periods. What do I mean by that? Well, that database sometimes has to be updated through maybe customer information, and the data will go into a holding table, but you don't have, new data can't get in during periods. So there's periods when that data repository, you know, whether it's OSI or Teradata, Hadoop or HANA, whatever it happens to be, there may be limitations in latency getting the data. Missing or incomplete data. That's an issue that you can go in and go, oh, where's the data? It ain't there. So in some cases, you know, you don't, when you do reads or you're trying to get data, you don't get it all. Even in interval data, billing data, what you do is you go back and reread it, meters that, you know, that you didn't get due to collisions or whatever. Well, a lot of this voltage data, if you don't get it, you know, let's say the meter was down or you just couldn't get it, you wouldn't go back and get it. It would just be blind data in the database. If a meter is not responding, you don't know if a meter was out, you know, under an outage, or was it broken, or was it not even there? So you don't know why you're missing or getting incomplete data, and that affects the analysis. The data repository, you can have ambiguous storage. Well, you have different vendors' data going in. We have multiple meters and meter vendors with utilities that I've worked with. So the values may not be defined. You know, voltage goes in. Well, is it over an hour? Is it 1 second? Is it min? Is it max? If you don't have the values defined, it really limits, you know, how you can use the data. And again, if there's data coming from multiple vendors, data may be different, maybe measured differently. So if it's not well defined and everything, the data repository has ambiguous data. You can get duplicates. So the data can be, you know, downloaded from logs once a day, but then if you go out and read the data for different applications, you can all of a sudden get duplicates that can foul up the analysis application. Another limit constraints is the as operated network connectivity model not exposed to an AMI analytics system. And I can't overemphasize the need, the importance of a network connectivity model. You know, if you're going to do analytics, you need it. Remember, we're talking about, it's some millions of meters, millions of nodes, and yeah, there's data, but if you don't know how everything is all connected, the value goes down. So, and not only an as built, but as operated, because especially during faults, you're switching, things are happening, you have to know what's connected to what on a near time basis. Communication's not designed for T&D related traffic. We talked about the latency, but it's not necessarily designed for real-time traffic. And that's the way it can be, but you have to work within the constraints and use it accordingly. And lastly, some folks put all their voltage data in MDM, and there's so many restrictions to getting the data. That aspect of an architecture is something that should be changed. So these are current constraints. So when we're talking about an architecture, to do it, we're talking about keep it simple, minimize it. Change is inevitable. These things are going to change very, very rapidly. Yeah, that I just want to speak more a little bit about that. These are new analytics where they're not fully baked. All right, so they're going to be added on or changed on a regular basis. So you're going to have changing what you got. You're going to have new operational applications for the data. The data coming in from new meters will have new properties, and there'll be new kinds of data. Major manufacturers are coming out, including Itron, with distributed intelligence, where there's going to be, new, very precise, important data coming in, so they're going to change. With new applications, there's going to be new latency requirements. Things may need to be coming faster. And then there'll be new client and server interfaces. One that comes to mind is DERMS. So with distributed energy resources, you're going to have new applications, to serve those new functions. And also with ADMS coming in and their own new applications, there'll be new interfaces and new ways. So change is inevitable. You've got to implement the foundational activities. And what is that? Well, first of all, we talked about the connectivity model. That's good. But we also have to now make sure that we know the meter to transformer, to structure, to phase mapping. Structure, because you have multiple transformers on a structure. So you have to have that in place. And again, the network as operated connectivity model. So you want to minimize latency, and you certainly want to design in bellwethers to accommodate a bunch of the use cases you're going to need. Now, bellwethers are going to be used for many things, and keep in mind when you're looking at a communication system that the notion of getting, regular reads in 5-minute, couple of minute kind of intervals will be important. You shouldn't be restricted by contract, whatever, in getting bellwether data. Foundational consideration is also the last one. T&D to provide detailed, highly specific functional requirements of the applications. So it's always the thing of at the front end of making sure that transmission and distribution, that you clearly describe the application you want to do, latencies, the data, and as well as the analytics to ensure that the architecture can support it. But if it's not detailed, you can find out there are restrictions. So now we come back to what is the architecture for leveraging AMI? So the needs. Analytics are evolving, so enhancements will regularly occur, as we talked about. T&D applications require data to be analyzed in near time, and AMI data needs to be correlated with other operational systems. That's the need for doing these new things. Now, what's the recommendation? The recommendation is a dedicated AMI advanced analytics engine with the embedded use cases. The issues associated with implementing AMI analytics in current existing operational systems are, just using regular words, it takes time. So if you have OMS, ADMS, DERMS, these are your operational systems. To get a change into them, you have to put it in the roadmap. It can take years. The cost is fairly high to put in new analytics in these systems, and the testing is extensive. So, when you make a change to your SCADA system or your DMS system, you have to, test every part of it. It's an operational system. And there's also a risk that when you're making these changes, can something go wrong? Well, if it's in an encapsulated engine that you can make changes to, where the engine is a server to these clients, it reduces those problems. You can make changes quickly, the testing is faster, the risk is lower, and certainly the cost of making these changes is far less. So, because AMI is new, that's the recommendation. So you can see here is a very high level view of the advanced analytics engine. It supports the analytics, it interfaces with your operational systems. And the first stage, in our view, is, you have a screen in grid ops. So to do some of those use cases like energized down conductor, instead of, tripping the breaker immediately or going into the operational system, you start to work it where, it's a screen in grid ops where they can get the information and act accordingly. Later on, then you will now have the client applications where you can interface directly into ADMS and the other functions. Now, this is just an architecture. The other one was highly simplified, but this is the general architecture that you may want to look at. But the key here is that all the data from the meter head end system goes directly to the engine, number one. There's no ETLs, there's no rounding about. The engine doesn't have its own database. It'll still store it in the regular database, so it's not a big overhead. But it gets the data when it comes in quickly. Then the engine also has a thing to the left called a web call constructor. Now, that's an important part of the analytics in that when the analytics are doing work, for example, energized down conductor, it gets in those exceptions, right? But then it may want to go out and proactively read the meters. Why? Because not all exceptions make it in. Maybe only 70% come in. So you want to verify that you've got all the meters that were affected by the wire down. Number two, when the exception comes in, the voltage value in the exception is that 1 second RMS value. Well, is it exact, or is it a compilation? And so you want to go back and read the meters and say, well, give me your voltage right now. I want to see what it is. And so this web call constructor is important, that the analytics engine says, here's the information I got, but I want to go out and get some better information. Okay. And then you see the rest of the interfaces, getting the data and delivering the value. So the architecture is not overly complicated, but there are components that are important to it to make it all work. So there you go. So at this point, hopefully I've given you some overview of how you can leverage AMI networks for distribution communications, talking about what it measures, how the AMI communicates, some of the use cases, and the underlying architecture. So again, we'll talk or have the Q&A session in a little bit, and you can ask questions then. And that's it. So right now, I'm going to pass it over to John Lamp from Itron, because one of the notions was, the idea of leveraging your AMI. Can I leverage the communications for distribution, beyond AMI? So John, you'll be talking about that, and I'm going to pass over the mic to you. Ari, can you get on?
Thank you very much, David. I always learn so much listening to you. That's really, really great. Thank you. So as David said, I'm going to talk a little bit about the network, and I see it kind of as the plumbing, which enables folks like David and many others to deliver great applications with tremendous business value to utilities. Next slide, please, David. Next slide, please. Thank you. So why are more utilities using or considering using their AMI network for distribution use cases? It's partly to increase the AMI ROI, and it's also partly due to new use cases, including both head-end analytics that smart folks like David and others are pushing us to develop, and also applications which run locally, which David also mentioned, on the distributed compute resources via peer-to-peer communications. Next slide, please. So utilities are now asking for medium voltage devices to talk to low voltage devices, such as meters, but also other new devices coming out. And partners have been reaching out to ask each other if their devices, both low voltage side and home area network side, can talk directly to meters in order to enable new capabilities, new monitoring, new control. So we need to coordinate across these different domains that used to really be separate. The medium voltage devices, the new low voltage devices, such as line sensors and voltage support and so on, meters, and also, of course, the home area devices, the DERs and other devices, EVs sitting behind the meter. Can all this be done on the AMI networks? Yes, it can. Next slide, please, David. So here are just a few examples of the range of current use cases and types of devices that are out on distribution networks today, running actually on the distribution electric network, but running on the AMI communications network. And there's a range of kind of polling frequencies and report by exception modes on the right. And you'll see that in the table on the right, there's usually different classes of service designed for different classes of those distribution field devices. And I'll come back to that in a minute. Next slide, please. So depending upon your available backhaul, your regulatory, your legacy situation, security posture, and so on, utilities may choose different takeout options. These can include using cellular only for AMI backhaul, in which case a new SCADA takeout device might be added to complement the existing network, as you see in the center diagram here. You could also possibly have some cellular for direct SCADA backhaul direct to the device, as shown on the as shown on the right, and the cellular backhaul for aggregated devices as shown on the left. So both options. So backhaul is one of the many choices in the degree of how much infrastructure you share or don't share between the distribution field device use cases and the AMI meter use cases, meter to cache use cases. Next slide, please. So although you can use the same radio technology, you're building a network with several classes of service. And you can also choose to share or separate different elements of the infrastructure of those networks between the sub-networks or classes of service, depending on your requirements, your budget, your comfort level with sharing or not sharing these things. Next slide, please. Some of the DERs of interest, of course, will be behind the meter, so it's important to be able to leverage the AMI network to at least monitor those. There are several suitable technologies, including using the AMI network directly, as shown in the right diagram, for things like direct load control. And then Wi-Fi from the meter is also an increasingly popular choice to talk to those devices, as shown in the center diagram. So many different choices. Thank you. Next slide, please. Although, again, as you may use the same radio technology, right, for your AMI and your distribution use cases, there are a number of different differences in how the AMI and distribution portions of the RF network are designed and therefore how they perform. We covered the infrastructure sharing choices earlier, that impacts the performance. And the different types of prioritization are clear, right? Prioritizing, distribution traffic over AMI meter to cache traffic. And as I mentioned earlier, it's key to understand the role of the network design. Next slide, please. The distribution network design process is different than that of AMI. I'm not going to walk you through all these process details, but it's usually a series of meetings between the customer and the network vendor to gather requirements and ensure that the distribution network design meets the customer's particular application needs for each class of distribution field device. Next slide, please. And the distribution classes of service on your AMI network will meet the requirements to which they're designed, and it's possible to have sub-second round trip times from control center to device and back if that's required. This is just a range of different deployed networks. There's obviously many more out there, but just a few examples to show some of what's possible today. Next slide, please. As I mentioned at the beginning, right, there are many new use cases require distributed compute, and David also talked about that a little bit. And having those resources available for local processing in addition to the peer-to-peer and central communications that we've discussed. Given the way that these requirements are evolving, it's usually best to make network platform decisions which allow for the possibility of distributed intelligence. You may want it, you may not, but you certainly want to have the option to add it later as you go forward in your projects. And this isn't new. Many utilities have been doing peer-to-peer local control of reclosers for years. Next slide, please. So finally, we've seen that there are many options to consider when leveraging the AMI network for distribution applications. One of the benefits of leveraging that infrastructure is the resiliency and redundancy of having multiple paths to multiple takeout points, which is afforded by the density of infrastructure enabled when you put multiple applications on the same platform. And that lets you hit your ROI goals. It's also important to enable emerging use cases which require local peer-to-peer communication and local compute across the medium voltage, low voltage, and home area domains in order to enable you to manage the grid edge as it continues to evolve. And now I'll pass it back to Ari for the fun part of our session today.
Okay. Thank you very much, John and David, for this interesting presentation. So moving on to the second part of this webinar, let me just put myself as a presenter here. And Zoom. Okay, I'm just gonna move to 47 quickly, sorry about that. Didn't work as the practice. Here we are. Sorry about that. So thank you again for the presentation, John and David. Moving on to the second part of this webinar, we'll go over some of the questions that you guys have been typing, as well as provide an overview of some of the offerings that Bridgewater Consulting Group, Itron, as well as CIARI can offer to guide you and help you with some AMI challenges. So for the AMI Rapid Review service, I'll let David continue and provide an overview on that. Following that, John Lamp from Itron will do the same to provide, Fred from Itron will provide an overview on their offerings, and then we will have an open Q&A session, and I'll read the questions out loud, as well as provide an overview of CIARI's programs that could be relevant to address your AMI needs. So David, I'll pass it on to you now.
Thank you, Ari. So Bridgewater, what we decided to do is put together what we call the Rapid Review Service. So Bridgewater Consulting, you can read it on the left, is offering a complimentary service to the utility webinars attendees to identify whether the utility's AMI and T&D infrastructure can support the data, communications, and system requirements of the use cases. So what we'll be happy to do is spend time with you and finding out if you can do it. You don't have to do it, but you know, we'll review your AMI infrastructure. Again, there's a lot of nuances, a lot of details. We can figure out if you got, you know, an infrastructure that can support what you need, and then also on the T&D IT side, can it deliver, you know, with the right latency and with the right data in the right time frame. So we're willing to do that, and I'm looking forward to it. We have a couple of folks that'll work with me, and I'm looking forward to, you know, if any of you folks want us to come in and take a look at what you got and where it can go, yeah, we'll do it. Thanks.
Thank you, David. To provide an overview on Itron's Grid Ops Quick Start, I'd like to introduce Fred Burnham, who is the Senior Product Manager of Itron, where his responsibilities include managing Itron's grid operations outcome during his time. At Itron, he also managed Smart Grid Analytics application and was a principal engineer for T&D Solutions. Fred has over 33 years of experience in the energy and utility industry sector. So Fred, welcome, and please feel free to take it from here.
All right, well, hello, and thanks, Ari. I mentioned I'm a product manager here at Itron, and I'm responsible for our grid operations analytics. And I just want to describe real quickly here what we can, how we can build on this data analysis that David and the Bridgewater team described to really demonstrate some of these use cases and their value using data from your utility. You know, it's one thing to show you the math and some case studies and things like that, and they're indeed, you know, impressive analytics. But to get the real value, you need to have this working in an operational environment at scale, day in, day out, to really drive that value and enable that at your utility. And we do this with what we call Quick Start. It's our rapid pilot program. So this is a cloud-based analytics system that enables us to stand it up real fast. With the cloud-based, you know, you don't need any special IT requirements on your end, and we do all that support. It's cost-effective, and it'll allow us to do, you know, demonstrate, you know, the results of these analytics. I'll talk about the data that you provide, but basically we'll enable the full access to these analytic results with web interfaces, custom query tools, additional training and support to prove out these use cases that we identify. And what you need to provide really is just access to these AMI readings. We're AMI system agnostic, so it could be any source of data. We could hook up, you know, directly to your head end, as David described, to get that data directly. Or in a demonstration case like this, we could even use a file transfer or some of those things. So that's your AMI data. And then the additional other thing, you notice that most of these analytics are based on a connected model, basically, or a grid model. And so you provide that in some form. We've got a couple of standard imports. And here's an example of some of the pilot use cases that we can do. The grid connectivity I mentioned, sort of the basis of everything here. Good connected models to perform all these analytics. And as David talked about, we've got a lot of EV and solar going into a lot of areas, things like that. And those really can turn these, you know, traditional feeder operations and stuff upside down. So detecting the EV and solar, the location of those, there's quite a few aspects for whether for programs or safety or impact on the grid, and how those affect your transformer loading, your other feeder loading, and those impacts on voltage. So these are all types of analytics that, again, this cloud-based system, we can stand it up fast with minimal data on your end and start proving that data out. So we'd love to work with Bridgewater with their assessment and move right into some of these and start demonstrating that value for you on a pilot type arrangement. That's what I had.
Thank you very much, Fred, David, and John. So I'll just provide a quick overview of CIADI's distribution programs that are relevant for AMI. So as I mentioned, we have 22 distinct programs. Just gonna go over some of the programs that currently AMI is being addressed from, you know, different perspectives. So looking at the Smart Grid program, the Smart Grid program is looking on the technological and system software, so, you know, ADMS, OMS, DERM, SCADA, decentral automation, so on and so forth, to really help you with grid modernization topics. And using AMI could be a good way to approach these. Each program in CIADI is identifying together with the members the focus areas that are currently relevant to them and that they need guidance and help with. In Smart Grid, they're listed here in the screen. We were looking at grid operation with DER and with new load types, such as electric vehicles, distribution automation deployment strategy, devices and technologies for distribution monitoring and measurements, integrating utility operating systems, so OT with enterprise IT. So typically we'll have engineers, specialists, emerging technologies, as well as IT engineers to look at the communication as well as the technical challenges, you know, monitoring and so on and so forth. We're also looking at building and maintaining the network model, its governance. We have a few projects and information on file. And we also look at utility transformation to support modernized operation of the grid. So using AMI, getting all these data, what kind of utility transformation is required to do it successfully? Who are the people that, you know, taking different roles and responsibilities, looking at data management, data ownership, governance, and so on and so forth. Another program that we have within the distribution sector is the distribution line asset management program. So the typical representation there is, design, engineering, planning, looking at asset management, maintenance, procedures, and so on and so forth. The main mission of the DLAM program is to address best practices and processes regarding the management of distribution grid assets, including planning, purchasing, installing, commissioning, maintaining, and operating of the assets. And similar to the smart grid program, the four main focus areas are to improve reliability of distribution equipment and systems, maintenance and assessment of distribution assets, technology and equipment impacting the grid, as well as power distribution planning. Also, we have the power quality and advanced technologies that recently it looks like the advancement in the AMI technology could provide good value for power quality engineers. So in the power quality and advanced technologies, we have the following three focus areas: customer power quality, so looking, at behind the meters, all sorts of power quality issues that utilities customers are reporting to and want to seek for help and guidance in order to improve their power quality. System power quality, looking at general voltage sags, swells, harmonics, and other typical traditional power quality issues, as well as the new stuff. So the new sensors and new measurements, how can you use that systems with good communication and system like AMI to improve and optimize your system in terms of reliability. And the third focus area is operational monitoring, metering, and related data analytics. So all of these are tying to AMI from different perspectives, and we are collaborating within our programs internally to see the bigger picture and network and help with other power utilities. Last but not least is the protection and control program. So this program, unlike the other one that are focused more on the distribution sector, is actually covering vertical power. So from generation, transmission stations, and distribution, looking at all sorts of protection and control issues. And I already seen some questions to look at, how does AMI can improve down conductors, wildfires. So of course, protection and control engineers will be interested in it, right? And so the protection and control is looking at the following focus areas. So protection and control management asset strategies, planning, training, and processes, protection and control testing, maintenance, and commissioning, design standards, protection philosophies, good utility practices, lesson learned by NERC, who are our members, automation, digital station, and smart system, looking at IEC 61850 and providing guidance on how to digitize your substations, and new and emerging protection technologies, such as the AMI presented by John, as well as David from today, and compliance, looking at software tools to comply with all the different international standards that is required. So that was it for me. Again, if you have any questions on any of these topics that we provided, such as technical questions for ITRON, for Bridgewater Consulting Group, for myself about membership, please don't hesitate to contact any of these persons here. I saw many questions asking, will this presentation be recorded? Can we get a copy of the presentation slide deck? So absolutely, we will provide a slide deck following this webinar. All attendees will get a copy, and you are encouraged to share it with your power utility colleagues. In terms of the recording, so it will be available to CIADI's members only. But if you have any questions or you'd like to hear some more information, we'll see what we can do there. Please feel free to reach out to myself. My name is Ari Kellenson, for those who joined in late. So what we'll do now is actually I'll open a poll, just a 1 or 2 minutes poll, to see if you like any one of us to approach you and make sure that we can help you with your needs. Any questions, some demonstrated utility experience. David and John here, as well as Fred, have lots of experience. They worked with SE for, more than a decade. So I'm gonna open that poll. And then following that, I'll start reading the questions that some people have already typed. And please feel free to add more questions as I open the poll, okay? Thank you very much. Here we go with the poll. I guess I'll start reading questions. David, what do you think as the polls are running? So start reading some of the questions based on the order received.
Great.
So first question for you, David, is how can you tell a downed conductor versus a fuse that blew up? Using AMI, of course.
That's a good question. I turned on the video, but I'm not. You can't see me, can you? It doesn't matter. So the question was, how can you tell a down conductor from a fuse blowing? Was that it?
Yeah, basically using AMI system, how can you identify that that the problem is a downed conductor and not just a fuse that blew?
Okay, so the question really has to be addressed in two ways. First of all, 3-wire versus 4-wire. So a 3-wire, it's pretty simple that if the voltage goes to the square root of 3, we know it's a load side. That if a fuse goes, you'll get a voltage divider that'll be 1/2 the voltage, for example.
Mm-hmm.
And so on a load side, real easy. On a line side or a source side, a little bit more difficult. But you look at the most upstream, you know, meter, and you say, oh, is there a fuse there? Could it be a blown tap? So the voltages vary a little bit. So there's a little bit of analysis at that point that says, did the voltage go up or down or whatever? Mm-hmm. But you can tell if it's a fuse blown or not. In a 4-wire system, when you lose, again, you look at where the issue began, and if the wire goes down and the voltage goes up, that means you've lost load. And on a 4-wire, the meters go to 0. And if the voltage goes up, that would be normal in that, yeah, you just lost load, you have less I2R losses. But if the voltage stays the same or goes down, you know there's still current flow, and that's indicative of a wire to ground. So, and again, you're looking in the network connectivity model where the fuses are, where the switches are, and if it's at a different point, you have a pretty good handle on, yeah, it's not a fuse that blew.
Mm-hmm. All right.
Do you have access to current? If you have access to the current, you could obviously tell if there was a fault or not before the voltage variation. Just a thought.
Yeah, in terms of the pre-fault, we don't get it from the current meters. Now then there's a new generation of meters coming out that may do, you know, pre-fault current. But if the voltage drops, you just get the voltage. You don't get in the arguments that come back from the exception, you don't get the current. And you don't know what the current was right before. So that's a limitation of the existing systems right now. In the new systems, you'll have it.
Thank you, David. Moving on to another detailed question. Are you aware of utilities that have integrated their AMI meter data directly into their ADMS or OMS so that the control operators interact with their ADMS, and HMI to monitor meter last gasp and leverage the topology that exists in the ADMS for outage response? Or do most utilities have separate AMI interface that control operators have to interact with? Now, I think we addressed these questions a while back, but I think it's a good question relevant to all attendees. So,
yeah, most OMS systems are still dependent upon phone calls coming in. Mm-hmm. I'm not going to talk about ADMS because that's an emerging kind of thing right now. I'll touch on it, but let's focus on OMS. That most OMS systems are based upon phone calls coming in and the operation of switches and breakers. What's happening is these power outage notifications are acting literally like a phone call, and they're being put in as a phone call, if you will, into the OMS. So the first part of it is many utilities, I would say most, that have AMIs have actually, have actually
because the poll was running in parallel, the system couldn't show the thing. So nice to see you guys.
So most OMS systems have the ponds and perns going into the system. But because of A, you don't get all of them, you'll get a portion of them, and B, you can get duplicates and things like that. They take them and they kind of bake them, you know, for a period of time before they upload to OMS. So most of them do go into OMS as a phone call kind of thing, but there's usually delays in trying to get rid of duplicates and integrating with the phone calls. So they're used, but with the perimeter analysis, they can be used more effectively. With ADMS, it's kind of new yet, that some ADMS systems are fairly new and they're starting to bring in the data pretty much the same way that OMS is.
So as a clarification, David, if there's a new utility that hasn't started yet, your recommendation is to add it as a separate monitoring tool within the control room, not to off the bat integrated with the DMS, is that right?
No, my suggestion is that the ponds and perns go into the engine, and then the engine delivers a package in near real time to OMS. That it would be integrated in their OMS system. But the front end analysis of what do these ponds and perns mean, let the engine take care of it, develop the thing, develop the footprint, and hand it right over to the OMS system.
I agree. If I could add to that, I agree with David. It's really good to have some business rules that filter that data down for the OMS. It's a great design that David was mentioning, and I completely agree on the ADMS or DMS side, right? It's early days, and there's a lot of data that you know. So you definitely, similarly, architecturally speaking, similarly, you're going to want to probably pre-process or filter it down. And I'm not aware of a lot of folks who've integrated much data that way yet, but you can definitely see it coming.
Okay, thank you guys. Another question is, did you use any AI or ML algorithms in any of the use cases presented?
So it was after the analytics were done, some machine learning was done. I'm an old, back in the 90s, and I used fuzzy logic and neural nets and expert systems and AI to do stuff. The machine learning and AI are really good for analyzing the data, but it's not baked yet to be part of the operational system. You don't want your operational system to be doing things based upon AMI. You want it to be an expert system, if you will, where the rules are validated using machine learning, maybe, but then put in bounded and clear and not changeable. You don't want things to be changing on the fly when you're doing operations. So the answer to that is that AI and some machine learning was done after the fact, after we did the research, but it's not part of the operation itself. There we want to what's called you don't want to use a self-organizing system. You want to use a knowledge-based system, an expert system with defined rules that are bounded and can be tested.
Thank you, David. What are some of the typical business case justifications?
The business case, well, today we're talking, the two biggies today is reliability. The business case is safety. Yeah, you can talk about O&M savings and things like that, but the idea of reducing the duration or the fee, the frequency are the number one. I think John's nodding. Yeah, you know, the PUCs and everything, they're really concerned about that, and that's the modern grid. We're supposed to have, you know, a more reliable distribution system. So the biggie is SAIDI. You will experience some O&M savings, O&M. For the West Coast here, we've got the two items, and that is public safety, wire down, and number two, wildfire. So those are the outstanding ones that are occurring now.
Well, that makes sense. Thank you, David. Let's see, there's a bunch of other questions. There is a remark from a member utility saying that you could pair the AMI measurement with the fault current measurement directly from the circuit breaker relay. So I guess if you have that circuit breaker relay, a suggestion that something that you could do to pair that with AMI. Any comments on that, David or John?
I've been talking a lot. John, you want to grab? I have an idea. John, you want to go first?
No, I think the context, sorry, I think the context to me was clear that it's talking about the down fault versus the fuse, right? So we had a question, and this remark is as a way to be able to distinguish between a downed conductor versus a fuse that blew up. So his suggestion is that you could pair the AMI measurement with the fault current measurement from the circuit breaker relay.
All right. That's a complex question. So first of all, when the circuit breaker trips, there's the fault current exceeded, obviously, the circuit breaker. Now, the circuit breaker is going to try to reclose. So two things can happen. One, it can reclose and lock, stay in, or it can lock out. All right. If it locks out, all the meters are out. I mean, they're going to get on-offs maybe and stuff, but power is down for that circuit. If it closes back in, that's scenario number 2. So if it closes back in, can you use the original fault current? And the answer is probably not. Most of the faults that I experience, first of all, when you have a wire down, you generally have a breaker operation prior to the wire down. What happens is Mylar balloon goes between 2 wires. You get the breaker trip, the wire goes down, but then the breaker comes back in and stays in. It says, well, I don't have excessive fault current. Same thing with the tree and other operations. So in the majority of wire downs, you'll get a breaker operation prior to the wire down, but the breaker will come back in. And now you have the wire on the ground. So using the fault current, because the fault current will relate to the initial Mylar balloon or line slapping, may not be correlated with what's occurring after that event. So I'd have to think about it. I don't have a good feeling that you can use the two because I think they're separated. And also be aware when there's a wire down, this is an important point, 25% of the wire down, energized wire down case studies that I worked on were complex, meaning there was a blown tap over there and a wire down over there. Because you had fault current due to some condition, blew a tap, but at the same time, a wire fell down. So you got to be careful. You fix the blown tap or you put in the fuse, but you can still have the wire down 25% of the time. That you can still have, they're complex. 2 things are occurring on that distribution feeder. Hope I answered the question, but I don't have a real good feeling about the fault current and then correlating it to the wire down.
That's okay. I think it provided a lot of clearance there. We can follow up also following this webinar. So thank you very much, David. An interesting question here is whether there is a standard for what AMI data must be captured to power quality prediction. Does this have a direct implication on the network infrastructure capabilities?
Read that again.
Is there any standard for what AMI data must be captured to power quality prediction? In other words, some standards recommendation for the data that you could capture with your AMI system to focus on power quality prediction or power quality monitoring. And the second part of that question is, does this have a direct implication on the network infrastructure and its capabilities?
Okay. Power quality, if you really want to get your arms around it, there's the IEEE 1159. That's a document on power quality. It talks about transients, momentaries, sags, surges, outages, low voltage. So power quality is this bucket of things. that are really not addressed by the meter. The meter's going to look at voltage, you know, in 1 second or longer, right? It's not going to do transients. Certainly not going to do, you know, really short-term, you know, 5-cycle sags. It's not going to do that kind of stuff. So what is the meter doing? It's really measuring voltage over a period of time. And yeah, you can call that power quality, and it is power quality. Oh, Stacy Williams is probably on here. He's a power quality guy at San Diego, but that is power quality, but it's a subset. So the standard is what you'd like the meter to do. There are no standards. You take the meter data and do what you can, but for me, the meter would need to look at shorter intervals than an hour. So a meter that either looks at only voltage over an hour or just captures the voltage at the end of the hour, which some meters do, they're very low value. But meters that do record 1 second values or max min during the hour have a real value in looking at power quality and predicting what the impact of power quality will be when you start correlating it with DER and the load, right? Start doing some forecasting, then you can say, we're getting a precursor to some real issues.
Thank you, David. So
could I add just to that just a little bit?
Sure, go ahead, John.
Yeah, and Fred probably could speak to this better than I if he wants to chime in. But as David said, I don't think there's a standard today, but there are certainly projects. People are working on this and doing projects to better understand what's going on in the power quality and seeing what they can learn from the meter, right? And I think that's what you need to do is, right, you need to do some real projects, and then you can develop a standard once you see what you can and can't measure and how useful it is, right? So I think it's a great question because it's leading us to where we need to go. But I don't think, as David said, right, I don't think we're there yet with a standard and this is all baked. But there are a lot of smart people looking at it, thinking about it, working on it. And so I look forward to us getting there. And then I think the other part of the question was about the network. I think it depends if you're trying to pull a lot of extra information back from a lot of meters to do this at the head end, then you would probably want more capacity in your network. But there's also a way to do it with distributed compute, right, on the meter to do some of the calculations there and pull much less information back. And that way, you know, you would have less impact on the network. So it depends on your architecture choice, right?
Yeah, I want to mention one thing. And I know there are people that are part of the AMI groups that are on this webinar. You're at a really important period right now of the manufacturers coming out with their next generation of equipment. They really are. We're at that cusp. And the notion of use cases by utilities of identifying what you want to do. Yeah, people say power quality. Oh, cool. If you can define those use cases and pass it on to John and Fred, they can get this stuff. You're at the perfect time to get it integrated into this next generation of equipment. So don't hold it, you know, inside, you know, communicate and let them know what you're thinking about, because it's the perfect time to let them know what the new meters should do. And these are big investments, you know that. They're big investments and they have to last for 15 years and stuff. So you're at a great time to say, this is what I want that meter to do, or I have this problem, can the meter do it? You there? Harry, we're not hearing you.
Oh, thank you. So I'll repeat myself. So just wanted to say thank you, guys. We're a little bit over time, so maybe 1 or 2 more short questions will make sense, and the other pending questions will be answered. I see some very detailed questions that we unfortunately won't have time to address them today, but definitely David or John will follow up and answer these questions. So a short question is asking, for downed wire prediction, what is the typical accuracy, and has the model been integrated in OMS?
So accuracy is based upon the work that was done.
Mhm.
Accuracy is two parts. One, did we identify and verify that was a down conductor? And two, what's our false positive rating? Because you don't want to, you can identify all of them, but then if you have 20-to-1 false positive, that doesn't make any sense. So the accuracy, given the full set of implemented rules, was very high. I don't want to give you the number, but it was very high if you had a full set of accuracy for a 3-wire system. 4-wire systems, we have the analytics, but the breadth of work has not been done yet to give you an overall accuracy. But on a 3-wire system, it's real good, real good.
All right, thank you. And last question for today. What are the typical latencies seen with AMI systems pre-processing data prior to sending data to an OMS or DMS? So how many milliseconds?
Yeah, so that's what I mentioned. So remember, it takes, X number of seconds for the data to come back. So now you got, and then a meter can blast out, but it can come from 2 directions, because it's just sending out a blast. So other meters can pick up that message and send it. So now you have duplicates. Sometimes perns can come in, restorations can come in before the ponds. Some goofy things happen. It's up to the utility to make that baking time. And the times that I heard were anything from 5 minutes to almost 20 minutes before that data would be loaded into OMS. I don't think you need that amount of time, but the question was, what do I hear? And that's what I hear.
And that's something, David, this is Fred, that often you don't want to act on too fast, in a matter of seconds or something. Even if you get that data, like you say, you want that soaking period a little bit to see, was it just a recloser operation? Can I learn a little bit more about isolating it and not just roll crews at the first outage notifications, right? So in that case, you really want that extra time to decipher it and sort of see what's going to happen if it fixes itself with a recloser or something. John, you've got cases that are sub-second, as you were talking about too.
Yeah. I was going to ask, I think absolutely everything that you guys said, friend David, is spot on for outage, right? You want to be a little cautious before you start sending trucks all over the place. Did the question specifically call out only outage, or was it asking a little more generally about latency? And I was also kind of wondering if it was asking about latency, in the network or in the head end or both, to make sure that we addressed what the question was really getting at.
Yeah, I think we'll have to follow up since the person who asked has left, but definitely, anything will be useful. Latencies for different applications that has to do with AMI, ADMS, OMS, I think will be valuable to members. So we'll follow up, and if there's any additional questions or follow-up questions to some of the questions that were answered, just feel free to contact any one of us. The slide deck will be shared. All our contact information will be there on the last slide. Thank you so much for you guys, David, John, friend. I really appreciate it. It was very interesting. And for all the attendees who took time today and join in with us, stay safe, and we'll follow up.
Thank you for putting, Siati, for putting this together. We appreciate it. And my buddies from Itron, it's great.
No, thank you, David. Thank you, Siati, and thanks to all the attendees. We really appreciate your time and interest.
Thank you, guys are very welcome.
Okay.
Have a good day, guys.
You too.
Bye-bye.